All right, so this last example that we're looking at is going to look at it from the numerical perspective. So in this set of notes, we've looked at particle motion and velocities in these application problems using the rule of 4. We did the verbal description, kind of talked about the understanding of what we're doing. We've talked about the graphical description. We've looked at it algebraically with looking at the formulas, and now we're going to look at a numerical table. All right, so the problem that we're looking at in example 8, we have the values of the x-coordinates, the values of the coordinates s of a moving body along a line. Now, so we don't really know whether the line is horizontal or vertical or diagonal or anything like that, but what we do know is its distance to the positive position or negative position, either a forwards or backwards from some starting position. And so they're giving you the coordinate of it along the line in whatever direction that it traveled in. And they're asking you to estimate the velocity at each of the following. So because you're estimating velocity, what they're asking you to basically do is to estimate, say, v of 0.5 or v of 2.7 or v of 3.5. So they're asking you to find these velocities. But basically what you're supposed to remember is that velocity is nothing more than the derivative of the position function. So if I want to estimate v of 0.5, basically all we're going to do in this problem is find an estimation for the derivative. And if you remember the derivative, how do we estimate derivatives? We basically use the symmetric difference quotient and show that the secant line slope is an approximation for your tangent line slope. So v of 0.5, which is equal to s prime of 0.5, we are going to approximate by using the slope of a secant line. And you do want to use the symmetric difference quotient when you are looking at these problems. So you want to pick a point on either side of your curve. So like even though there is a point for 0.5 and 35, I don't really want to use that point on the curve. I want to use the 2 points, because if I use like this and the one after it, kind of exaggerating it here, that would be the secant line slope. Whereas the tangent line slope that I really want is this one right here. And a better estimate for that, especially if the curve is smooth and continuous, is pretty much always going to be that if you pick a point on either side and then draw your secant line there, this will be a better estimate to that. So that's why we always pick that one. Instead of picking the 0.5 and 1, I'm going to pick 0 and 1. Now you do want to make sure that when you show your work, you're showing the difference quotient that you use so you get credit for it. So we're going to do s of 1 minus s of 0 over our 1 minus 0. So you want to show that you know you're using an average rate of change to estimate an instantaneous rate of change. Now it doesn't really matter whether you show it using the function notation or you could show it by actually putting the values in, and you could do your 30.2 minus your 40 over your 1 minus 0. It doesn't matter which of these you show, but you must show one of them, and then you must go to your final answer, which, you know, if this was a calculator problem or not a calculator, this isn't that hard. 30.2 minus 40, negative 9.8. Now do not walk away from this problem until you actually put units. Now remember, this is velocity, which is change in y over change in x, change in position over change in time, so this would be in feet per second. Okay? If you are asked to interpret this, again, just kind of stressing the whole 5 parts of the interpretation, you would say at t equal to 0.5 seconds, the particle's coordinate is moving in the negative direction at 9.8 feet per second. Notice that I didn't say increasing or decreasing here because or left or right or up or down because I didn't really know where the line was going. So that's why I used the terminology moving in the negative direction, whatever that direction happens to be. So here's the when, the what, and which way, and how much with your units. Right? And then so the rest of this is fairly straightforward. B is essentially the same thing. If you want to estimate your velocity at 2.7 seconds, you're basically doing the derivative of the position function at 2.7 seconds. And so your difference quotient that you would show for that, here's 2.7. And again, we don't want to use that. We want to look on either side a symmetric difference quotient. And so we're going to do our S of 3 minus S of 2 over 3 minus 2. And again, I'll leave the calculations to you. You could show the actual numbers or you can show the function notation, and you end up with minus 10 feet per second. And then now the interesting thing here is at 3.5. Now you'll notice that you didn't have 3.5 and neither do you have a symmetric difference quotient that you can use. So based on the table that you have, the best that you can do is going to be probably 3 and 3.6, you know, kind of thinking about if it's smooth or not. Here's your 3.5. 3.6 is close. Maybe 3 is over here. You could use that, or you could use the 3 and the 4. You know, kind of what might be a better estimate? I would probably, I guess as long as you justify, I'd probably go more with the symmetric difference quotient. So even though they gave me this 3.6, I might kind of go ahead and go with I'm going to use the symmetric difference quotient again over this. So I'm going to do V of 3.5, that a better estimate for it is probably going to be the symmetric difference quotient. So again, equals S prime of 3.5, and I'll use the symmetric difference quotient of S of 4 minus S of 3 over over 4 minus 3. 4 minus 3. So we're going to have 0.2 minus my 38.2, so you're going to end up with negative 38 feet per second. Okay, so again, the idea here is that whenever possible, you're going to use the symmetric difference quotient. Now, if I didn't really have anything that was symmetric, you will see at times, I don't think they'll be that unclear on the AP, where you might use these two if you didn't have the 4, because it would be in between. Okay. All right, now example 9, our last example, and that's just something to bring in because it really is kind of an application. Those of you that have been in the econ and personal finance class have heard these terms before: your marginal cost, your marginal revenue, your marginal profit, and then average cost. Now, marginal cost is loosely defined as the extra cost of producing one more unit. So right now you have a current cost. So we have a cost function that describes how much it costs to produce X units. And so you have a certain current cost, and then marginal cost is going to be how much will it cost you to produce one more unit. Marginal revenue is going to be the extra revenue that brought in from selling one more unit, and your marginal profit is going to be your extra profit from making and selling one more unit. So the idea is that we're basically looking at profit. Profit is revenue minus cost. And then our average cost, that's a little different. Our average cost is basically saying, well, right now, if it costs me, say, $100 to make 5 units, then if I take 100 divided by 5, it's going to tell me the average cost per unit at that moment in time. Okay? Now, what they're doing here is just an example to work through. So suppose it's going to cost, here's a nice little polynomial, so we know it's differentiable, it's continuous. And it's going to produce this, it's going to cost us this much to produce X radiators. Now, what's important here is that this is only valid for 8 to 10 radiators. And this is a made-up problem, so it's very, you know, unlikely, but maybe that's the cost, because maybe after 10 radiators, maybe we need to add a new factory or buy some new equipment or find a new supplier for the metal that we're going to use to make the radiator. So something happens after 10. So maybe right now we have a current setup that can make 8 to 10 radiators every time that we produce it in a day. And so that's our kind of idea, that if we wanted to produce more radiators, then what we would need to do is have more labor, have more equipment, have more supplies. All right, so we don't really know what's going on, but we know this is our cost function for 8 to 10. And this is our revenue function for 8 to 10, how much money we're going to make on the radiators. And again, if you'll remember, your revenue is a changing function, because the more supply that you have, then usually the price drops, okay, because The glut in the market is going to mean that there's plenty around, so there's no, kind of has the incentive the price is going to drop. Whereas the less radiators that you have, the more that they're in demand because there's few and they're rare, that means your price is going to go up. So the idea here is that your revenue is dependent upon how much that you are actually selling. So when you have X radiators to sell, this is how much revenue you can bring in, because that will kind of have an idea of how much price you're going to be able to charge for them. All right, and so your shop is currently producing the maximum 10 radiators per day. So they're doing the absolute max they can given their supplies, their labor, and their equipment that they have to use. All right, so then we're going to go through and we're going to learn some things about our factory and how we're doing. All right, so I want to calculate the average cost of producing 10 radiators. So I'm trying to calculate the average cost of 10 radiators, which means I'm going to take the cost of producing 10 and I'm going to divide by 10. So, all right, just basically it's a plug and chug. You're going to put it into plug in 10 up here, calculate it. You're going to get $550 is how much it's costing you that day to produce those radiators, maybe in your labor cost and the electricity for running your equipment and the supplies that you have bought, and you divide that by 10, and so that's going to tell you that it is currently, at this moment in time, costing you $55 per radiator in your production cost. Right? And then you're like, okay, well now how much am I making? So on average it's costing me $55 per radiator. So now I want to know what's the profit of producing and selling 10 radiators. So we're trying to find P of 10, and if you'll recall from the formula above, your profit is found by taking your revenue for 10, how much are you actually getting for 10 radiators, and you're going to subtract your cost of producing those 10 radiators. So again, that's simply a plug and chug problem. So we're going to get 820 is the revenue that we take in, and our $550 is how much it's costing us. So we're going to make a profit of $270 for those 10 radiators. So we must have probably an $82. We're selling them $82 a piece. It's costing us $55 to make those 10 radiators at that moment in time. So we are making a profit of $270. Now, the question that then comes up is, well, should I go ahead and make one more radiator? If I could push my people to make that one more radiator, is that going to be beneficial to me? Do I want to expand my business? So some of the things that they're looking at in trying to determine whether they want to increase their production is, well, the first thing they're going to do is they're going to look at the marginal cost. And the marginal cost is how much it is to produce one more unit. Now, the problem that you have, and this is because you can't really see into the future, this is what you know your cost is only for 8 to 10 radiators. We don't really know necessarily what's going to happen in the future. So we're basically trying to use what's happening now to help us predict what's going to happen in the future. And so we're trying to figure out, we want to produce one more unit. We want a cost per unit to figure out how much more. Should I only look at the average cost? I mean, right now it's costing me $55 per radiator. Now, if I don't really have to increase, maybe I don't need any more labor or supplies to make this. If I could hold steady on all the kind of fixed cost of what's going on in my factory right now, if I could just squeeze out one more unit, that would be great, because my cost would still be $550, but I would have 11 radiators that I'm making, and that would of course be much better than the $55 per radiator that's costing me currently. The cost per radiator will go down. So then the idea is, well, how do I find a marginal cost given that I don't really have an idea of what's going to happen in the future? So we have this cubic function that's giving us our cost of radiators. So I'm just going to kind of put a generic graph up here. So suppose this is my C of X. And we don't really know what's going to happen after this point in time. So we know that it works to about right here. And I'd like to kind of have some information about what happens, what would the cost be at this moment in time, what would the cost be to produce one more radiator? The idea is that dollars per radiator is basically a slope, right? You're basically saying, well, if I could look at the rate of change of how the cost is changing at this moment in time, then that slope could give me an idea of the marginal cost. And then you think, well, wait a minute, the slope of this tangent line, that's nothing more than the derivative at 10. So I basically, if I could calculate C prime of 10, then that could give me an idea of the marginal cost. You don't know what's going to happen in the future. If the curve were to continue, we could say that the cost, we could actually calculate, hey, I think my costs are going to be following the same function. I could do C of 10. Or I could estimate it by doing the derivative, and that would give me, because when you are close to 10, the tangent line is a good estimator of the cost function. And so the idea is we're going to look at what's happening right now as opposed to trying to make up something that's going to happen in the future. And we're going to use what's happening right now to determine what our marginal cost is. So basically what we're going to do is they want to show that the marginal cost when 10 radiators are produced is approximately the cost of producing one more radiator after 10 have been made. So marginal cost is going to be the derivative. So let's first go ahead and calculate the marginal cost, C prime of 10. Now to do that, I really need to calculate the derivative. So let's go ahead and calculate the derivative up here above. Your derivative would be 3x squared minus, just using the power rule, 12x plus 15. So that's the rate of change at any point on the curve. And so the cost of producing that one more is I'm going to calculate what's my rate of change at 10. So I look 3 times 10 squared minus 12 times 10 plus 15. And so that marginal cost is going to give me, I didn't do my calculations before I started the video, so we have what, 300 minus 120. 300 minus 120 would be 180. And 180 plus 15 equals $195. And so that's $195 per radiator. So if the trend continues, then an estimate of what my marginal cost would be. Now we don't really know what's going to happen in the future, but we feel like it would cost us about $195 per radiator. Now, if I look at the kind of average, which is C of 11 minus C of 10 over 11 minus 10, that idea is kind of looking at the slope of the secant line in between these 2 points. We can actually figure out, well, what would be the average increase, the actual cost, if that were the function to continue. And so C of 11 minus C of 10, plug in 11. Right, and then our C of 11 ends up being 770 minus my C of 10, which I calculated above, which was 550. Of course, over 1 is going to give me $220 per radiator. And so the idea is, are they close? Yes. Are they the same? No. And that's because your slope, your instantaneous slope, using that as an estimator because this curve is concave up, is going to underestimate. And again, why do we care about using the derivative instead of actually calculating? Because we don't necessarily know what's going to happen in the future. So instead of saying that this is going to be the curve that's going to continue, we're going to basically say we're going to look at how fast we're changing right now, and we're going to use that information to make ourselves kind of a plan of action from there. So keeping the same idea, if I want to talk about the marginal revenue, so marginal revenue, what they're basically going to do is they're going to calculate the derivative of the revenue function. So we're going to do R prime of 10. We want to see, well, how much money would we be making? If I look at how fast the money's coming in based on the revenue function, I want to determine, well, what would that do? Would that be a good thing in order to produce that one more unit? Because I definitely want to make sure that the revenue that comes in is going to balance out the cost that I have for it, right? So my revenue function, we need the derivative for that as well. So I'm gonna, let's see, where do I want to put it? Let's go ahead and not do 10 yet. We'll do that second. So we'll do this as R prime of X. And so our derivative of the revenue function, 3x squared minus 6x plus 12. Okay, and so we want to see what's going to be the marginal revenue for selling one more unit after the 10. So we're going to look at R prime of 10 and do that calculation. All right, and so that's going to be $252. All right, so basically, should our company begin producing and selling, and that was per radiator, make sure we have our units on there. So should we begin producing and selling 11 radiators daily instead of 10? So the idea here is, well, first let's look at our profit. Our predicted profit, since the revenue we took in was 252, and our marginal cost is going to be 195. So our 252 minus 195 is going to give us a marginal profit of $57. And so the idea is based on our current costs and our current revenues that we have coming in, we are going to make a profit. We're going to make a profit of $57. Now, but that's really not enough to answer the question, should we produce that one more? Because there are other factors that are going to affect this decision. In order for me to make one more radiator, do I need to hire one more worker in order to get this done? And if I hire that one more worker, how much does it cost me to pay that worker for the day? And is that going to eat into the profit? Because the question is the cost function going to continue? Well, it depends. You have to look at other factors and determine, well, do I need to purchase more supply? Do I have enough supply in order to make one more radiator? Do I have enough labor to produce one more radiator? Do I need to add more labor? And if I add more labor, of course, my costs are going to go up. Is my factory or my shop equipped enough to make that 11th radiator? Or do I need more equipment? Do I have more capital costs that I'm going to need to do? And so the idea is it's not just the idea of looking at it in terms of these derivatives. There are other factors that might affect our decision, but we can certainly use this information to help us make that decision.